Yeah, I think we can move to Q&A. So, questions? Sure.
Hello?
Is it working? Okay. Here.
Yeah, please.
That was a very good talk. Thank you, Doctor. And I had a question about gauge theory, I suppose. So you were saying you could understand that the way we see time dilation is that we're moving kind of like a organized cluster on the hypergraph that seems to be persistent. And so I guess it's the same thing for a particle.
Okay, so, yeah, right. So the question is, how do you get gauge theory out of all of this? The answer is, we don't entirely know, but we have some idea. Okay? So what happens is, you have this hypergraph, and, okay, what is gauge theory? What the sort of the key mathematical idea of fiber bundles, where you have a base space that is something like physical space, and you have fibers, and in the fibers are some internal degrees of freedom that are, have a structure that corresponds to, let's say, a Lie group or something. And so the question is, how do you take this hypergraph and decompose it into sort of degrees of freedom that correspond to the base space and degrees of freedom that correspond to the fibers? And we are really close to figuring this out. But we have not really quite, it's quite a lovely thing, because what you end up getting is, so the big thing that makes a gauge field is the connection between, when you have two fibers, you have kind of the structure of the, where you are in the group on one fiber, where you are in another fiber, and you have to make a connection that gives you a covariant derivative that lets you move around between those things. Okay, so we just have, actually very recently, a very lovely construction of the covariant derivative in the limit of these hypergraphs. And it goes through a few steps. I mean, and basically what we have to build is a new version of geometry that starts from hypergraphs rather than starting from Euclidean space, which is the usual way things start. But so we're not there yet. I mean, one thing I will say is that we don't really know what particles are in these models. And I was feeling really bad about this until I realized that in particle physics, you don't really know what particles are either. And so, nobody actually talks about the full structure of a proton. People talk about, when you do Feynman diagrams, for example, in particle physics, or in quantum field theory, you have these lines that represent the propagation of an electron, let's say, from one interaction event to another interaction event. What I realized actually fairly recently is what Feynman diagrams they are causal diagrams that represent the causal relationships between interaction events. So the electron interacts here, then it propagates and interacts somewhere else. And so you can think of them, Feynman diagrams, as causal graphs, and you can think about, I will say one, and that allows one to have a much lower level view of kind of quantum field theory than one has when one actually tries to think about the lines representing particles. Actually, I have to say, when I was younger, I knew pretty well Dick Feynman, and Dick Feynman would always say, because I did a lot of work with Feynman diagrams in QCD and things like this, and he would always say, this Feynman diagram idea is really a stupid idea. He said, there's got to be a better way to compute results than to use these crazy Feynman diagrams. And actually, I remember I once worked out that the kth order of Feynman diagrams, the computational complexity of working them out goes like k factorial to the fifth power. And it's like crazy complicated. There's got to be a better way to do this. Well, I think we maybe have a slight clue about what that might be now. Because you can think of, but also the fact that you can essentially construct quantum field theory or without ever having to talk about what a particle is. And as I say, I don't feel as bad about that, because in actual quantum field theory, you now have to talk about what a particle is. You just think about the incoming states and this S matrix and then the outgoing states. And you never really talk about, there's a big fluffy proton there or whatever else. And sort of conceptually, you imagine something like an electron as a point particle, whatever that means. It has no internal structure. In these models, that won't be the case. An electron will have a big, complicated structure. Actually, to make another comment, my guess is that black holes are closely related to particles, something that I suspected when I was a kid, and I was told that was a stupid idea. But in any case, the feature of black holes is that outside a black hole, they're only the mass and spin parameter and maybe charge of the black hole matter. All black holes are equivalent, at least after a while. There's no kind of, black holes don't have funny extra mountains on them and things like this. And so that's also one of the mysteries in particle physics, is why are all electrons the same? And I think that in a black hole, you could have some complicated civilization that got crushed into a black hole. Inside the black hole, behind the event horizon, there's a whole crushed civilization. But you don't know it because on the outside, it's just the same as any other black hole. My guess is that electrons work the same way. That in fact, that sort of inside an electron is kind of pieces of network that are different between different electrons. But to the outside, it looks the same. And my guess is that the way that sort of electrons arise in something like this hypergraphs is going to be very similar to the way that black holes arise. So that's a few thoughts. But maybe that wasn't even what you were asking. I'm sorry.
It wasn't, but my PhD is going to be involving a lot of Feynman diagrams and Feynman integrals, so I can agree.
Sorry, it's hard for me. It echoes a lot, so it's really hard for me. I think if you just say what you're... Just don't use the microphone. Just say, yeah.
I was also going to ask if you felt that, in light of the fact that gauge theory can be seen as kind of a redundancy in our description, that maybe because the hypergraph theory may inherently be some sort of custom observable, you wouldn't need to resort to gauge theory to sort of chart interactions. That's what I was going to ask.
Okay, that's an interesting thought. I think that so the question is, the point being made was, the story of gauge theory is a story of different possible ways that you can kind of slice things up. So different ways, the quintessential kind of gauge theory is general relativity, where you can have these different ways of kind of deciding what corresponds to simultaneity in space and so on. And I think I think what we know about observers is far too coarse to say there is a preferred gauge. It is also, the thing to realize about a lot of these things are independent of things. For example, a common statement about relativity is there is no preferred reference frame in the universe. But this is manifestly false, because the cosmic microwave background has a definite center of mass. And so it's, there are things where there is a theoretical reason to think about things as being theoretically independent, but then in practice it doesn't work that way. And this may be very much the same kind of thing, that there is a preferred gauge defined by the way we are as observers, but nevertheless the structure of the theory one can work out on the basis of the fact that it's independent of what the gauge should be. That was a fairly technical question. I'm happy to do technical, non-technical, any level of technical. I'm sorry. Please, over there.
Hi. Thank you for that.
You want to try and catch the...
Who is it?
Try. Good.
Hi. Thank you for the lecture. Last week, David Tong was giving a lecture here. It was about our chiral universe. And I remember he talked about an interesting theorem, maybe the Nielsen, Mia says that our universe cannot be simulated by a computer since the existence of chiral fermions. Yeah, and
this is crazy. Honestly, this is one of these things where if you build, you have a whole collection of assumptions, and then you say, given that collection of assumptions, it's absolutely impossible that it could work this way. I'll tell you a story about that. These cellular automata that I've studied a lot, there were theorems that said one-dimensional cellular automata can never do anything interesting. How could that be? They obviously do lots of interesting things. The problem was that in setting up those theorems, people had, put in all these assumptions that basically, chopped out. One of the things that is actually an important thing about doing computer experiments is computer experiments keep you very honest. I've done computer experiments for years. Every time I do them, they show me things that I did not expect were there. I mean, my kind of line about this is usually the computational animals are always smarter than we are. You know, you have an idea about what's going to happen, you actually run it, and you find out, oh, it happens in some totally bizarre way. I'll show you one example, a very recent thing that I did. It's actually not, will be out in a few weeks, hopefully. Let's see if I can. Okay, so here's an example of something where, you know, you're trying to make a, you're trying to get a cellular automaton rule that will make red, blue, yellow. Okay? I never would have guessed that way that it did it, the second one, where it has alternating red and blue stripes, and it happens to line up in phase to produce red and blue. So it's very dangerous. These impossibility theorems have a very bad history. And I could quote you many such impossibility theorems. I would not, I mean, this particular thing about chiral fermions, that just sounds like nonsense. I mean, I know how chiral fermions work, and there are various features of space-time that, okay, so, I mean, this is a tower of kind of detailed technicality that, that leads one to, okay, so, okay, I'll give you one flavor of how this works. Let me think how to do this. Basic point, for example, even number dimensions, odd number of dimensions behave differently. Well, this is going to get, let me see if I can think of a path through this that isn't hopeless. Let me think. No, I mean, there's a thing called gamma 5, which some of you might have heard of, which comes up into rack algebra. I don't know, do people know about this? Somebody knows about it. Okay, it's when you have totally antisymmetric things, they behave differently in even and odd dimensions. In particular, if you try and imagine, I don't know, this is hopeless. I'm sorry. I'm trying to, you know, sort of attack something very technical, and I won't be able to do that in a simple way. And I don't know the specifics of what was being claimed. I have heard. Did you mention Nina Mia? Was that the name? So, yeah. Okay. I remember him from 40 years ago. Yes, sensible guy. But I mean, I love these impossibility theorems. There was one that said that it was impossible to make, you know, renormalizable gauge theories, actually. That was another, you know, with mass, that was another impossibility theorem. Let's see, what other impossibility theorems can I quote to you? People said it was impossible to make a thing like Wolfram alpha. That wasn't quite a theorem. That was a folk result from the history of AI. So that's a terrible answer. I'm sorry. I usually like to give much more explicit answers, but that's probably the best I can easily do. Please. Oh, let's have a few more. We'll add some. Please. Okay, so the question was, how does one bridge liking physics and being an entrepreneur? The thing to understand about both research and entrepreneurism is that the thing that tends to matter most is figuring out the strategy for what you should do. So people do, you know, learn about science, physics, whatever else. A lot of the time, people really concentrate on learning the mechanics of how to do physics. But actually, what determines success in research is not being able to do the mechanics the best. It's whether you have asked the right question, have the right strategy about what you should do. And that turns out to be a very similar thing to dealing with kind of the entrepreneurial world, is do you have the right strategy? What is the thing you're building? Is it a product that anybody cares about? In both cases, there is sort of an environment you have to be in. You know, if you're an academic, for example, I have not been an academic for 38 years now. If you're an academic, there's a certain sort of rhythm of life that you have to be adapted to, so to speak. It's different from the rhythm of life that you should be adapted to if you're doing entrepreneurial kinds of things. Like in academia, you know, there are lots of committees that figure out this and that thing, and you're probably not personally responsible for this or that thing. If you're running a company, you're personally responsible for this or that thing. And that, for me, you know, I like that much better. I don't mind being personally responsible, but for other people, it's much more comfortable to be, we're just in this collective thing where I don't have to take full responsibility for that. But I think the thing to understand is, about making products, if you're going to make a product you want. Because people sometimes have this idea, I have this idea, I know there are people who want this, I don't want it myself, but I've been lucky in a sense that the things I built as products, I use every day. Actually, we have a difficult situation right now because we're building a product, first time ever, where we're building a product that I am not in the target market for, because we've managed to make a kind of AI-powered teaching system, initially for teaching algebra. Okay, so that was a long time in the past for me. When I try and use this thing, it's horrifying. It's like this would drive me totally crazy. But so it's difficult for me because it's not a product that that I would use myself. So that's a thing to understand. I think that the kind of what you need to be good at doing research is remarkably similar to what you need to be good at doing sort of the strategy for entrepreneurship. There is also the mechanics of entrepreneurship, of managing people and so on. The typical thing that happens, I have to say, with science people doing entrepreneurial kinds of things, is that you have good analytical skills, you can think your way through all kinds of problems, but for some bizarre reason, people disengage the thinking apparatus when they come, when they're dealing with business kinds of questions. And it's just bizarre because the people who are, very analytically capable and they have some issue with people or some such other thing, and they're like just not thinking. And if they were to apply those analytical skills, it would work well. But that's a typical kind of failure of that. Maybe we can have one or two more questions and then we should wrap up.
Yeah, sure, actually. Why not? So
I see one way at the back there.
Oh my God! Yeah, sure. Go ahead.
Oh, okay, really way at the back. Okay, well let's take those two and let's make that be it.
Here we go.
Thanks. Hello. I was wondering what kinds of experiments you can do to test this hypergraph theory. You mentioned something about a non-integer number of dimensions causing observed effects that would not be caused by other things. Is that the only thing, or are there other things you could also?
Well, this is a challenging thing.
What experiments would you do?
It's an interesting problem to figure out what the other effects might be. I mean, I've been trying to figure out what kinds of effects one might look for, so have a bunch of other people. The dimension fluctuation is a pretty good one. There are other ones, like, for example, if you have a critically spinning black hole, there will be a difference in the shot noise. If you have gravitational radiation from a critically spinning black hole, the shot noise will be different in this model than it is in continuum general relativity. However, observing the shot noise and gravitational radiation is pretty far away. So that's not good. I have a suspicion that there are differences in correlations in photons in orbit around black holes. There'll be some different behavior there, but that's also rather hard to observe. Then there are things with black hole mergers that are possibly, and we're trying to kind of, sharpen up our efforts to simulate black hole mergers, because there's probably some additional effects there to do with the ring down after a black hole merger that are different. The reason they're different is because in our models, so the speed of light determines the kind of, given a certain amount of time, the speed of light determines how far you can get in physical space. In our models, there is one other kind of thing, which is the maximum entanglement speed, which is, given a certain amount of time, how far can you get in branchial space. Actually, there's really only one parameter in our models, which is either the maximum entanglement speed, the elementary length, the elementary time, the elementary energy. They're all related. There's just one free parameter. Basically, when black holes merge, you pretty much, the thing is you have to, it's limited, the rate of that merger is limited both by the speed of light and by the maximum entanglement speed. And that means there are different effects. But of course, we don't know the maximum entanglement speed, which is annoying. I mean, I have some possible estimates, but I have no real confidence that they're right. I mean, they come from various rather hokey arguments might suggest that the elementary length is around 10 to the minus 100 meters, much smaller than the Planck length. That it's clear it's much smaller than the Planck length, but how much smaller is not clear. So the other possibility, the other possible vector is in many-body quantum mechanics, everybody is rushing towards trying to make quantum computers, which I'm not sure is going to work, because I kind of think that in this picture of quantum mechanics where there are these sort of many threads of computation, there's this problem that you have to knit those threads of computation together to actually get a definite answer that we say is the answer. And in the standard formalism of quantum mechanics, that's not really taken into account. It's just you apply a measurement operator and then the thing happens. The maximum entanglement speed determines things about that knitting together of different quantum threads. And so I have a faint hope that the current sort of noise floors and so on that are observed in actual quantum computer efforts, that those are related to the maximum entanglement speed. I might be quite wrong. I might be off by 50 orders of magnitude, and it might be that there's still, lots of engineering mess between kind of the what's actually observed in quantum computers and the floor that you would expect from maximum entanglement speed. I mean, kind of the analogy I've been using is if you were making telescopes, you could imagine your telescope would have infinitely high resolution if only you could make the mirror better. But in fact, we know that diffraction limits the resolution of telescopes, and this maximum entanglement speed is not the same mathematics, but it's the same concept, that it's a fundamental limit on how you can knit together those kind of quantum threads. So there's a few thoughts. I mean, I think that the dark matter thing is another one that if we could figure out that the details of how that works, which is quite challenging, that would be a really good test, because there's a fair amount known about the behavior of dark matter, including some slightly anomalous kinds of things, and their sort of their parameterizations of modified Newtonian gravity and so on that you can kind of plug into. So a few thoughts. I mean, it's difficult because the underlying theory is very simple, but working out its consequences is really quite complicated. And it's also, as a sociological matter, complicated theories and complicated experiments, it's a difficult business. I mean, famously, piece of history in 1916, after Einstein invented general relativity in 1915, in 1916, he had a prediction for the bending of light around the sun, and some people were going to go out and observe that, and a total eclipse in Crimea. Well, they were Americans, and the US had just entered World War I, and they were turned away because the Russians didn't want this weird equipment there. So they didn't do the experiment. The experiment was then done in 1919, but by that time, Einstein had kind of fixed the calculation. It had been wrong. If the experiment had been done in 1916, then they would have concluded general relativity is wrong, because if they'd been able to do the experiment well enough, it wouldn't have agreed. In 1919, the general belief is that the actual experiment that was done was kind of fudged, and that it was, right answer, but they were very, very keen to get the right answer. So it's always pretty difficult. This merger of experiment and theory is kind of complicated. I mean, I can tell you one story, actually, from when I was a kid. I worked on QCD and worked on production of charm particles and proton-proton collisions. And so I'd worked out kind of the rate of charm particle production from proton-proton collisions. I had some answer. And then there was an experiment that was done which said, no, there are no charm particles produced at a rate less than 1/5 or something of what I'd predicted. So it's like, what do you do? Either I'm pretty sure that my calculation was right given how QCD works. And so either QCD is wrong, that might be one thing you would conclude, or something else. So I wrote this paper which is sort of half about the calculation and half about the experiment and why the calculation might be wrong. Well, needless to say, I'm telling you this story because it turned out the experiment was wrong. It's always a difficult experiment when somebody says, I didn't see any. It's like these impossibility theorems. I didn't see any particles. Well, the question is, how did you look for those particles? And in fact, they were looking for them in slightly the wrong way. So it's a tricky thing, lining up experiments and theory. Okay, maybe one last question and then we should wrap up. But I think there was one back there. Unless there was one right, I think there was one. One of them is over there, so it might be close to one. Okay, Sorry, sorry.
There was one thing that you said that I didn't really understand, and that was that from your theory, both general relativity and quantum mechanics sort of arise naturally.
Yeah.
Given that in their current state, we know that there's several contradictions between them, how can both theories arise from the same set of...
Sorry, there's several what?
Several contradictions between general relativity and quantum mechanics. How can they arise from the same set of rules?
There aren't contradictions. It's just that the mathematical apparatus of quantum field theory, when you kind of just try and take the things we know about gravity and import them into the kind of theoretical framework of quantum field theory, it doesn't work. But that's taking the kind of traditional theory of gravity, importing it into the traditional framework of quantum field theory, which is not what we're doing here. Because we have a different formulation of gravity, we have a different formulation of quantum field theory, and those match up very beautifully. It's just that given the formalism that's been built now, it doesn't match up. But given this sort of lower level formalism, it matches up very nicely. And you can start to see, I mean, there's a bit more, there's more detail to that, but you can, I mean, well, I'll give you an example of a place where those don't match up. So in quantum field theory, there's a 0 point energy in the vacuum. Just like quantum mechanics says there's a certain amount of uncertainty in everything, and among other things about which there's uncertainty is how many particles are there. So in the vacuum, there's always this bubbling number of uncertain number of particles. That leads to, so one of the big sort of contradictions is that means that there is a whole bunch of energy in the vacuum associated with those 0 point fluctuations. That energy in the vacuum is such that if you took that seriously and just said there's this energy in the vacuum, that would curl the universe up into a tiny ball. It's incompatible with the structure of general relativity. How does that resolve in our model? The way it resolves in our model is that the things which are like the low-level version of those quantum fluctuations are what build the structure of space. So in other words, in the traditional model, you've got space on the one side, which is curved by the presence of energy, and then you've got quantum field theory on the other side, where you're generating all this energy as a result of uncertainty in quantum mechanics. And those are two different theories, and they're incompatible with each other. But in our model, what happens is the structure of space is made by essentially those quantum fluctuations. So there is no incompatibility. And it's not like you're importing one thing into the other and it doesn't work. They're both part of the same underlying structure.
So are you claiming to have solved quantum gravity?
What's that?
Are you claiming to have solved quantum gravity or unified quantum gravity?
Yes.
Well, I hope you get your Nobel Prize soon.
What's that?
I hope you get your Nobel Prize soon then.
Maybe one day if I live long enough. No, I think people, this is the thing that happens in fields, okay? When fields are young, if you'd said that 100 years ago, nobody would have laughed. Because people at that time thought one was absolutely on track to figure out how quantum mechanics and gravity would fit together. 100 years later, everybody thinks, oh, that's too difficult. It was, its foundations. We know that can't be done. And so it's and this is what happens in fields. It's a feature of older fields. If you look at young fields, like, for example, machine learning a few years ago, everything was kind of still on the table. It wasn't like, we just know it doesn't work that way. We know it's impossible. This is a feature, it's a feature of the fact that, as I said, physics 100 years ago, general relativity, quantum mechanics, statistical mechanics, they were all born 100, 120 years ago, that kind of time frame. And at that time, it was, there was no tower where people said, oh my gosh, we can't climb this tower. And there has been such a tower. I think the things we're able to do with this kind of computational approach kind of give one a new way to think about things. And by the way, the approaches people have taken, whether it's spin networks, causal set theory, a variety of other kinds of approaches, turn out to plug in really nicely to what we're doing. And it's actually sort of interesting. I didn't think it would work that way. I thought it was kind of either us or them, string theory or what we're doing. It turns out we're pretty sure, not properly nailed down, we're pretty sure string theory is a particular limit of these hypergraph rewriting models. Certainly spin networks are a particular limit of that. Certainly some of these other causal set theory is another limit of this. So these things which people have developed, often they're rather frustrated because they haven't been able to find any kind of grounding for what they're talking about. They just say things like, there are random events in space-time, but we don't know why Lorentz invariance works because the typical random arrangement of events doesn't lead to Lorentz invariance. With our model, there's kind of you know why there is, you know why the events are arranged the way they are, and it leads to Lorentz invariance. So I think it's interesting, okay, as a piece of the arc of the history of science. The fact that people laugh when you say you might have solved quantum gravity is a feature of the particular place we are in the arc of the history of science with respect to physics. And I think the exciting thing the last few years is I think we finally broke kind of the deadlock that's existed for a long time. All right, I should stop there. Thanks.